Alright, welcome everybody. So this is our next chapter, Chapter 5, Thermodynamics. Actually divided into two chapters. There's a later chapter where we'll go into some things like entropy and Gibbs free energy. This chapter really deals with just the first law of thermodynamics. The first law of thermodynamics, the idea that energy cannot be created or destroyed, that there's a system and a surroundings, and that there's transfer of heat and energy between those two. So in this particular chapter, there are some definitions that you need to know. A lot of you know most of these already. We'll talk about what heat of reaction is, where that comes from. We'll also talk about calorimeters, and this year we're going to do some bomb calorimetry work. Bryce, don't get too excited about that. And we'll also do the Q equals MC delta T problems, and we'll do a little bit of a twist with that because we're going to be applying that to chemical reactions as well. And then we'll do some Hess's law problems. So let's go through and first talk about, what energy is. What's the definition of energy? And you might have a working definition, especially if you've done, some physics in the past. You might have, a good idea of what you think energy is. But, when I define it using, the textbook, I would say that energy, by definition, it's the ability to do work or give off heat. And, when we talk about heat energy, we need to have some, key points here about this. When we define heat, what heat really is, it's just this energy transferred from a hot object to a cold object, from a hot or higher temperature object to a cold slash, lower temperature object. And when we talk about work, work is the ability to move something, to apply a force to it, and to get it to move. And so we'll have a force times an acceleration. Now, there are different kinds of energy that we'll talk about. The two main ones that we really focus on are kinetic energy and potential energy. Chemistry is all about potential. Potential is what, when we refer to it, we refer to chemical energy. As there's a chemical change, bonds will be broken, bonds will be formed, and that's where the energy changes occur, during those bond formations and those bond breaking events. Now, if we talk a little bit about energy changes, we're going to need to know these two terms, because we always will refer back to these two terms over and over again. So the first one is the system. The system is the part of the universe whose energy change we're going to observe. So this is the part of the universe whose energy change we will observe. Generally, this is like our chemical reaction. And then the surroundings, this is everything else relevant to this energy change. So, together, they are the universe. The systems and the surroundings together add up to be the universe. Now, I'm not talking about the universe in the sense of the cosmos and galaxies far, far away. I'm talking about a micro-universe. If you have a beaker that's heating on a hot plate in a room, the universe does not include your house over in Seacliff, because the effect of those energy changes in your little micro-universe will not affect what's going on in Seacliff. Now, here's an example of system and surroundings. Here's some nitrogen and hydrogen gas in a closed container. And so here's my piston. And what I can do with my piston is I can apply a force. That force will do work. And so what I'm basically doing here is I am doing work to the system. So I'm putting energy into this system by applying a force by pushing down on the piston. Now, what that does inside here, we just did gas law. So when you think about this, the particles aren't going to be moving faster, but they will be colliding with the walls more often. And so although their force won't necessarily, increase per collision, the amount of collisions that they are going through will increase. So if I were to say, what's my system, what's my surroundings? So my surroundings would be out here. My system would be in here. Together, they make up my universe. Now, each particle that we see in a system, it has both potential energy based on its chemical makeup. That's what the potential energy is about, the chemical composition. And then we also have the kinetic energy, the movement of the particles. What you're going to see is that we generally neglect the kinetic energy once we get into something called enthalpy. We talk about the potential energy changes. When we have these chemical reactions, the reactants are going to be converted into products. And there's almost always a change in energy. And this change in energy, well, we're going to have two possibilities. You're either going to have energy that's released to the surroundings. What this means is that the energy of the system, final, is less than the energy of the system, initial. So when I look at this, my change in energy of my system, it's going to be less than zero. It's going to be negative. But my change in energy to the surroundings is going to be positive. So when you have something that is releasing heat to the surroundings, it will feel hot because you are the surroundings. On the other side, if I have energy absorbed from the surroundings, the energy of the system final will be greater than the energy of the system initial. And the energy of the system, the change in energy of the system will be positive, whereas the change in the energy of the surroundings will be negative. And again, this is you here. And because that's you, you're the surroundings, you're going to feel as though heat's being sucked away from you, and it will feel cold. Whereas if there is energy being released and you are the surroundings, it will feel hot to you. Now, what I'm showing you here are these different types of, changes, and this is just what we did on the previous slide. It's just a picture of it. So initial state and final state. This is of my system here. So my change in energy here, my change in energy is less than zero. It's negative. Energy is going to be lost to the surroundings. Here, the final state is higher, so the energy change is greater than zero, and energy is gained from the surroundings. What we're really interested in is the system, because the system is what we're studying. Now, we'll always try and go through and do two types of definitions that we'll talk about, heat and work. And I defined heat and work for you on the other page. heat is this what they call thermal energy. Oops, thermal energy. And a lot of times they'll give heat this symbol Q. And again, this is when energy is transferred. But now let's try and like look at it in terms of system and surrounding. So we would say where we have energy transferred between system and surrounding. And the thing is that this is based only on differences in temperature. And then we have this work definition, and this is going to be energy transferred when an object is moved by a force. So this again, we have our moved by a force. The thing is that in most chemical reactions, both are occurring. You have heat, you have work. You drive a car, it gives off heat, but it also is doing work. It's propelling you, it's bringing you places. And so we can combine them together. We can say that the change in energy is equal to Q plus W. Now, what's important about this is you have to, sort of pick a direction. And so what we'll do is we'll say this is change in energy of the system. And just be careful of the language that they use. And I'm going to talk about that language here. And the language is heat being given off, released, heat being absorbed, work being done to, work being done by. And those are the differences between them. So here's our heat possibilities here. So, like here we could have heat flowing out. And so this would be sort of like a situation if I were to take, if I were to have hot water, a beaker of hot water, and I were to put it on the lab bench. So I have my beaker of hot water. I put it on the lab bench. This is my system here. The lab bench, the hot water may be 100 degrees. The lab bench may be 20 degrees Celsius. Heat's going to flow out of the system until they reach an equilibrium state. I could have heat flowing in. So here I would have, simple scenario here, ice water. So now I would have, my ice water at 5 degrees Celsius and my, lab bench here at 20 degrees Celsius. And now the arrow is going to be going in here. So in this case, we would have a negative Q. The work is equal to 0. So the change in energy for this one up here is going to be negative. Down here, we have heat going in, we have a positive Q. We have work equal to 0. So we have a delta E equal to positive. Now what if we have a situation where we're doing work and we don't have any heat? So what I did was I have nice pictures down here. I'll show you on slide number 11. Here's the two situations. I'm just going to write that up here. So this is slide 11. Slide 11. If we go down to slide 11 here, just to show you what is happening is we're making H2 gas here. This H2 gas, it's going to push this piston up. So this is work done by the system. So here in this situation, slide 11A, the heat we're going to say is equal to 0, but the work is being done by the system. That means that it is negative, so our change in energy is equal to a negative value. If I go back and I look at pushing down the piston here, now I'm doing work to the system. So this would be B. Heat again is equal to 0. Work is done to the system. In terms of the system, it's positive. The change in energy equals positive. Rarely do we have just one or the other. Rarely do we have just one or the other. Instead, what we have going on here is a combination of the two. We just don't have work done by the system or work done on a system or to the system. Instead, we have a combination. So here's a battery running a fan, and so there's heat generated, but there's also work. We have a combination of the two. Over here, they're showing just heat. Overall, the change in energy is the same. One was used for useful work, cool somebody down using a fan. One is done just generating heat. So I'm going to stop here. Next time we'll talk about thermodynamics, conservation of energy, and we'll talk about what a state function is and enthalpy. And that'll be our next video. We'll go up to endothermic, exothermic. Thanks so much.